fatigue factors, fatigue failure. Okay. This is the factor on endurance limits. So we have learned that couple of factors. So this is okay. This n is n prime, the real coming from the experiment. Okay, this one. So we have load factors, we have size factor, we have surface factor, we have temperature, CT, reliabilities, CR, and then we have lastly, okay, that's all. So we have 1, 2, 3, 4, 5 factors which influence the experiment's endurance limit. Okay, this is the experiments. Okay, all these factors we could get from the tables given, depending on the load acting on that component. Okay, either axial, bending, or the torque also applied on that component. Okay. Then we have learned the type of loading on that material especially for the fatigue. Okay, so this is for fatigue stress. We have learned that it has three types of loading. Okay, three types of loading. One, this is reverse. Okay, fully reverse stress. The second one, we have repeated stress. So for the fully reverse stress, fully repeated stress, it has the characteristic for alternating stress and mean stress as well. So this is the characteristic for the repeated stress, where the sigma mean is 0. So we have like this one. The third one is fluctuating. So fluctuating. So here we will know that it has maximum stress, minimum stress, then alternating stress, and then the mean stress, okay, and then stress range. So this the different types of loading will have a different types of sigma max, mean, sigma A, sigma min, and radius stress range. Okay, then from this fatigue stress, we have learned this fatigue stress will modify if there is discontinuities or any notch, okay, any stress concentration on that component. So it will influence by Kf. Okay, so this is fatigue. This is fatigue, stress, concentration, which is we learn Kf. So Kf influenced by the equation of 1 plus Q notch and KT minus 1 for bending and axial, and if torsion applied, so we have KFS 1 plus Q KTS minus 1. So this fatigue means or alternating or maximum will be multiplied with this KF. Okay, this KF. Okay, then this KT, we could get the value of KT from the tables depending on the design of the components, any discontinuities, notch and the different shape, different diameter. Okay, so especially for the shaft. Okay, so we could read the KT from that graph. Okay, and then also we could get the value of Q, which is notch sensitivity from the graph as well. Okay, for bending and axial load and also the torsion. Okay, so if we have a couple of stress, we have axial, bending, and torsion. We need to combine. So we need to combine those stress. So here, let's say we put here, okay, this is one, this is two, this is three, this is four, this is five. Okay. Okay, I put here. Combine stress. So we combine, okay, we combine. So two types of combination, one for the uh, alternating bending stress for bending, alternating bending stress. So we use distortion energy theory. This is distortion energy theory. Sigma A axial plus sigma bending squared plus tau 3 times tau torsions. Okay, torsions. For the mean stress, we use maximum principal stress. This is for sigma means. Okay. Okay, so you could get from the equations. Okay, what for? Why we need to calculate this sigma alternating and sigma means? Because we want to relate between the alternating and mean stress. So we have Langer, then we have Goodman. Okay. For Langer safety factor, sigma A, sigma Y, yield strength, sigma mean, Y equal to okay. Safety factor is this one. If safety factor 1 is 1 lah. Okay. Then we have the graph X1. 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 For Goodman, we have sigma A ultimate strength, endurance limit, or fatigue strength, sigma means, and SUT. Go to 1. This is the graph for Goodman. This is sigma M. This is sigma A. Okay, this is sigma M, mean stress, sigma A. Okay. So this is safe to fail. Safe, fail. Right. Okay, this is what we learned last week. So now how we could solve the problem. So take a look on the question that I share with you in e-learning. That question is in somewhere here. Okay. This is shaft. So rotating shaft, both end have bearing, both end A and B, and the shaft is rotating, and there's a load applied on the shaft, 5 kilonewtons. So we have to decide either the shaft will save or it will fail in certain cycles. Okay, either it is has infinite life or finite life. Fail with in the certain cycles. If we use, okay, take a look. If you use Langes, or Goodman. So firstly, we have to identify the fatigue stress. Okay, because the equation for Goodman and Langes, for the Langes is sigma A Sy plus sigma mean Sy equal to safety factor. This Langes. And for Goodman, sigma A endurance limits plus sigma N safety factor. So both need to have the value of fatigue stress. Okay, so we have to determine the fatigue stress. So if we see here, in order to find the fatigue stress, so we have to follow the process, okay, of getting fatigue stress. What is the process of getting fatigue stress? So this either this alternating and main stress. So we need to define this one. And also first thing that we have to determine which is the most critical point, which is the most critical point here. So first we have to identify the reaction force at A and B. So free body diagram, then reaction force. I think this is not the problem. Very simple free body diagram, direct free body diagram. So you could draw free body diagram like this one. This is RA. This is RB. This is the force. F. $175. Okay. So moment equal to 0. Let's say take a moment A equal to 0. Then you will get RB, right? You will get RB. So RB times 500. So this 20 plus 280, 300, then 20 plus 180, this 200, this is 300, total 500. So RB 500 equal to 175. 325. So RB equal to berapa? 3,250 Newton. And after that, F equal to 0, okay, which means that RA plus RB equal to 5 Newton, 5 kilonewton, 5,000. So you will get RA equal to 1750. So you have done your free body diagram and the reaction force. So this reaction force is on the bearing. Yes, 5 kilonewton, 5 kilonewton. This F 5 kilonewton, yeah, 5,000 Newton. Five thousand. Okay. So then you have to draw. So in order to find the criticals, which the moment, okay, the moment which experienced by the shaft. So we have to draw the moment diagram. So we have to draw the shear force diagram, shear force diagram, and moment diagram. Right. Diagram. So shear force diagram, this is load. So you have load here, 5 kilonewton. This is RA, this RB. Okay. So you will have shear diagram, then moment diagram. This shear diagram, this moment diagram. So RA is 1750. RB is equal to 3250. All right. So 1750 straight, go down and to here. Then for the moment diagram, you need to multiply 1750 times the distance. So the distance here is 325. This is 175. Okay. So you will get the moment diagram like this one. So 325 multiply 1750. Yes, Rizwan.
Doktor, tolong tanya.
Ah,
Kenapa graf V, graf force kita,
graph V,
kita 5 V,
V, yeah.
kita 5 Newton ke bawah. So 1750 reaction top dia 1750 ke atas.
Yeah.
Tapi untuk section tu kita lorik yang bahagian atas, tak buat bahagian bawah.
Oh
Sebab
tak,
5000 tu
okay.
lah.
Dia sebenarnya dia lorik bahagian bawah sebab dia luas di bawah graf. Dia punya area tu luas di bawah graf. Luas di bawah graf. Di antara this one area, this one area, this one. Okay. shear dia, shear ke atas. Okay. Dan this one ke bawah. So kita lorek kat sini. This the graph dia. So kita tak lorek kat bawah ni. Lorek kat atas. Yang ini dia akan dia turun. Total, this one total is 5,000 Newton. 5,000 Newton. This is 1,000. The shear acting on that.
Betul.
Shear acting on the shaft.
Betul.
Okay. Okay, then moment 1750 times 325. So total 568,750 Newton. Okay, dia kena complete lah. Dia kena completekan dan turun kat sini. Sebab dia from zero kan. Come to zero. Okay, this is the area of force acting on the shaft. But we have to consider as well that we need to identify the critical point on the shaft. Because the shaft, it has the fillet. The fillet though, if you see the fillet, we have to determine either this is the critical or this is the critical. If we, from our naked eyes, this will have stress concentration, C-O-N, concentration. Okay. So we have to prove that this is either this is critical or this is critical. Right? So this here is the point of here is the point. Okay. So we get this value and we have to find this value. How to find this value? Because we have identical rectangular. This one. This distance, we know, and we also know this distance. Okay. This is one of the method. Another method is, okay, we try this one first. Kita tahu 568,750 divided by 325 equal to 325. This is 200. Okay, so we want to identify x value. So x divided by 200. So we will get the value of x is Newton. So another method that we could identify, not from this moment, so we just times the moment here, this R8 1750, okay, 1750 times the distance is 200. So we will get the same value. So for the moment acting, so at X, where here is the fillet. The value is 350,000 Newton. Then we need to calculate the bending. The bending acting on that fillet and acting on the force, on the force. So this is, oh, aduh hilang lah yang menyampah ni. Okay. Hopefully you dah kira. Okay, so this fillet is 32 times moment pada fillet pi d3, which is 32, and the fillet is 3050 divided by pi, and the diameter of the shaft, the smaller shaft. So the smaller shaft is 35 mm. Then we get the value of 83.15 megapascal. So please remember of the units. Please remember of the units. The best, either you want to convert, just remain the M, or the best thing, if you use for the Pascal, normally we in the mechanical we use megapascal. So for the megapascal, so we normally use unit is millimeter and Newton. So Newton millimeter. Newton times and the power of 4. So you will get megapascals. So the bending on the force, so the diameter is 50. So we got 32 times 568,750 Newton times pi. Diameter is 50 millimeter, power of 3. Then you will get 46.346 megapascals. Okay. So here we prove that the bending moment, the bending on the fillet is higher than bending at the force acting on the shaft. Okay, this is the criticals. So we need to proceed for this one, for further analysis. Okay, now we identify which type of fatigue stress. So we have 3 types of fatigue stress. Okay, we have 3 types of fatigue stress. If we see the condition is like the RR more, which is reverse bending. Okay, which is reverse bending. Reverse bending means like this. So reverse bending. So in reverse bending, we have this is sigma A, and this is sigma A as well. So sigma means is 0. So the value that we get is the sigma A alternating, the value of the bending, the alternating stress, the bending. So what we get is sigma A, this is the value, which is 83.15 megapascal. And sigma means 0. Okay. So this is alternating. Okay, this means steady. Okay, what next? What next? So we have the fatigue. We have fatigue stress. And then we identify that it has the stress concentration factor. We need to uh, calculate the KF. We need to calculate the KF. Before that, in order to calculate the KF, also we have to know the material properties. The material properties. Sampai dah. Okay. Okay, the materials, EISI 1020 HR. So you boleh tengok lah, you could see from the diagram, the tables. So SUT is equal to 455 megapascals or 66 kilo PSI. Or yield strength is equal to 290 megapascal. Okay, the next determine the stress concentration factor and notch. So the formula of KF is equal to 1 plus Q KT minus 1. So what is KT? What is Q? What is KT? What is Q? So we have to look on the tables. Okay, table here. So it only bending, and no torque. Okay, no torque. Tadi. Okay, could you see the tables, the graph for the KT? So in order to read the KT, the graph for the KT, you need to calculate first, because the x-axis is, you need to calculate R over D, and for the graph, so you need to calculate D over D. So R is the fillet, so the value of the fillet is, cuba you clear, value of the fillet is 3, and the radius is 35. And capital D is 50, and then 35. So you will get apa you dapat? Tiga bagi 35. 0.0. 0.0857. And 50 divided by 35. This is 1.429. Okay, boleh kelas, boleh follow. Okay, then boleh tak you baca? Could you read the graph? Berapa you dapat value dia? How much the value that you get? So berapa tadi? 0.03 apa value dia? Okay. 0.08, okay. 1.429, 1.4. So you see that the above is 6. Then the next 1.429, 0.0857. So above is 6, and then 3, and then is 1.5. So your value is 1.4, just near 1.5, just a bit slightly below 1.5. So you could take 1.5 graph as your guideline, That is take the third one, the third from above 1 to 3, 1.5. Okay. Then R of the x-axis is 0.08, 0.0, 0.0. Betul value 0.08. 0.08. So this is 0.1. Okay, the next, this value is 0.09. then 0.08. Okay, 0.085. So 0.085. So just go up, and this one just a bit below. So you could take 1.7, 1.7, 1.78. Boleh? Okay, 1.78 or 1.79. Okay, so take this, the third graph is 1.5. So your value is 1.4. That's a bit slightly below. Okay, slightly below here. Then your the x-axis R over D is your value is 0.08. Let's say 0.085 in the middles. Okay, in the middles. So 85 in the middles here. In the middles, just take that one. 1.78. Boleh? 1.78.
Boleh Dato', boleh.
Huh? Boleh eh?
Boleh, boleh.
Okay, that approximate value 1.78. Okay, then your KT is go to 1.78. Okay, then you need to calculate, determine the Q value. Okay, Q value is Q. Okay, the notch, the R value is 3. This 3. Okay, notch value is 3 millimeter. 3 millimeter. This one. And the material properties, ultimate strength for the materials for bending, which is in KSI. So in KSI, it has the value of 66. Okay, 66. So you have 6 here, bending and axial. So you have to take this here value. Okay, this is 60. So you even sometimes you could make the interpolation value, the interpolations. 60, this 3, just go up from 3, and this is 60, and this is 80, and the middle is 70, 66, just a bit down. You got 8, 0.8. So you could get 0.778. 0.78. Boleh? For the notch. Boleh ya? Faham? Okay, let's 0.78. Let's make it for 0.7. So Q is 0.78. Then KF 1 plus 0.78. KT 1.78 minus 1. Okay. Berapa nilai dia? Kira. One point 606084. Okay, good. Sama. Okay, we get KF. KF. Then what is the next? Okay, the next we guna ruang ni. So we need to multiply this value with the KF. So the real, okay, what call it, the real, okay, whatever names that you give up, then you A is KF times KA before, right? So then 1.6084 times 83.15. So this sigma m is 0 because KF times sigma m is equal to 0. So this is so you will get 133.74 megapascal. Okay, so you get this one, the alternating stress after considering the factor. Okay, so then you need to calculate the endurance limit SN by considering all the factors, modification factors. So sigma n CL times CG CS CT CR times SN prime. Okay. So Sn prime is equal to SUT for the steel times 0.5. So you will get SUT is 455 times 0.5 is equal to 227.5. Then we need to identify what is CLCG. Okay, let's take a look of the graph for all the factors. this one. Okay. Load factor, bending, 1. Then gradient factor, diameter. Diameter is, this is, the first one is less than 10 mm. So diameter here is the 35. So between 10 mm, the diameter of the shaft, okay, 10 mm, between 10 mm and 50 mm with 0.9. So we take gradient factor 0.9, load factor 1.0. Temperature factor doesn't state anything. So temperature factor take 1. Okay. Then reliabilities doesn't mention anything. So just take 1. Else if it's made in question mentioned that the reliability factor, considering the reliability factor is 95%, so you have to take this value. So otherwise, just take 1. Okay, the next is surface factor. So surface factor, this surface factor. Mention the rotating shaft shown in the above figures is machine. So this is a machine. So this is a machine. And we just need to identify the ultimate strength. So ultimate strength for the materials, KSI here, this is the matrix. So for the KSI is 66, right? 66, 70 in the middle, 70 in the middle somewhere. In the middle, this is 70, and this 60, 66, 66 somewhere here. This 66 here. Okay, so we could take 0.79, just a bit below 0.8, 0.79, not exactly 0.8, okay, because exactly 0.8 is 60, so it has 66, 70, 66 here, somewhere here, okay, so we could have a bit lower value from 0.8, so 0.79. Boleh? Faham Boleh?
Boleh, Doktor.
Okay. Okay, 0.9. So kita ada semua ni dan kita darabkan dia. So the SN we have 161.73 megapascal. Right. Okay, what we need to do before we insert the value in the equation using Langes and Goodman criteria. So the next step is the combined stress. We need to combine stress. So for in combining the stress, okay, in combining the stress, we have two types of combining the stress. One's using the for the alternating, we use von Mises stresses. Kita gunakan only alternating yang kita ada. So it means that sigma, okay, this is equivalent. This is equivalent. Equivalent. Sigma A tau kalau sigma means kita hanya ada, we just have the alternative stress because our mean stress is zero. Mean stress is zero. So we don't have any shear stress, top tau, we don't have. So we just only have the value of alternative stress, which is one to 133.74. 133.74. 133.74. Because this is zero. And we don't have sigma equivalent means. If we have equivalent means, we need to insert the value of sigma means using this formula. Tau plus. So this is zero. So in our case, this is zero. Okay, after that, just insert the value of Langes, which is 1 over equivalent A divided by yield strength plus equivalent means divided by SY. This is zero. This is 1 divided by 133.74. Yield strength. Yield strength is 290. Okay. Then for Goodman, we have 1 over sigma equivalent alternating divided by endurance limit plus sigma equivalent means divided by ultimate strength. Okay, this is 0. Is 1 over 133.74 divided by Sn. We have calculated the Sn. Our Sn is 161.75. 161.75. Okey, berapa nilai dia? Flanges. This flanges, Prem. Okay. Flanges 2.1684. Goodman. Goodman 1.205. Okay, 94. Okay. Okay, it means that shaft has infinite life for both. Okay. Based on Goodman and Lange's theory. Okay. Okay, that's all for equations for the calculation of the failure theory.
Doktor,
Any questions?
Doktor.
Yeah.
Macam mana kita tahu yang infinite life tu, Doktor, yang last tu apa?
Infinite life. Infinite life. Okay, kita consider infinite life if both get the value more than 1. Safety factor safe lah. Safety factor dia sebab kalau they get less than 1, if one of them get less than 1, like Goodman get less than 1. Okay. So if we calculate, we don't know, this is prediction, this is only prediction. Based on the Goodman theory, okay, the shaft is has the finite life. Maknanya it will break in certain cycles. But if the value is more than one, so it means that the shaft will never fail for life. Never fail. More than 1 is never fail. Less than 1, it will fail in certain cycle. So in certain cycle, we could calculate actually. Sebenarnya kita boleh kira which cycle that the shaft will fail. Kita boleh kira. Tapi the value kita dapat ni more than 1, both more than 1. So the shaft based on both theory. Kalau kita running the shaft is rotating using this condition where the load 5 kilonewton applied on that shaft. So we predict that the shaft will not fail forever. Tapi tak berlaku lah kan. This is prediction. Forever. The running material tu akan tahan. The material of the shaft tu will sustain, akan tahan, tak akan berlaku crack in that particular area at that point, because we consider that the critical point is between in the fillet between the smaller and the larger shaft. That is the critical point we have calculated. That's mean by less than 1 and more than 1. Infinite, more than 1, finite. Finite maknanya ada had lah, finite. Infinite tiada had. Kan? Dia punya kehidupan tiada had. I don't know what I'm going to say. That's it. Boleh Okay, boleh take any example. Same example lah. Same example. Same condition but different loading. Different loading and different type of shaft. Same material. Just all the same materials. Okay, ini sebagai you punya assignment lah. Nanti the next question ni saya akan discuss kemudian. Ini agak susah sikit. Okay, saya lukis je. Copy, you copy. Shaft. Saya bagi kemudian lah. Saya akan type soalan ni. I will give the question later. I will do the proper questions. Okay, class. And so far, any questions? Malas saya type. Okay. Okay, if you have a time, just do. Just think of. Okay, think of these questions. Okay, just think of the questions. The bevel, pinion, and ground finish. Okay, this is the bevel pinion. The bevel pinion means the types of gear. Bevel pinion. This is type of gears. Pinion normally smaller gears. Bevels, types of gears. have some angles. And ground finish shaft. This is the bevel pinion and ground finish shaft. Ground finish shaft means the material finish of the shaft. As shown in figures, bearing at A will fully support the axial loads. The axial loads. So later you will learn types of bearing. So types of bearing which support axial loads. FA, the left end of the shaft is coupled to an electrical motor. The left and the right end is free. Okay. Gear force act at 75. Okay. Okay, it means that this shaft is coupled using the coupling. Okay, coupling because coupling is the method of combining two shafts. Okay, using coupling. Okay, using coupling to an electrical motor. So the shaft is rotating using a motor. And load components applied by the mating bevel gear are shown. Means that here there is another bevel gears, which will the effect of mating the gears will cause the load on that bevel gears. If the material properties are ultimate strength is 900 megapascal and yield strength 700 megapascal, determine the safety factors guarding against fatigue and yield failure. Okay. So this fatigue and yield failure is Langes. Fatigue is Goodman. Safety factor because Langes is just yield strength. Okay, just yield strength. And Goodman is fatigue because it has endurance limits. Consider the endurance limit. But Langes, they don't consider the endurance limit, just consider the yield strength. The yield failure. Yield failure means tend to failure. Okay. So the same step that we have to proceed, but the first thing we need to identify the reaction force here. Okay. The reaction force here. So we could look one from this one. Another one we could look from this one. Okay. So when we look from here, this direction, we will, because we want the plane, okay, we want to see which plane. We don't have, you could draw X, Y, X, Y, X, Y, Z as well. Which plane, either X, Z or Y, Z. So otherwise, also you could use which direction that you want to see from. So if you see from here, this direction, so you will see for the plane, you will get this value. Betul? Kalau you lihat daripada sini, atas ni, this plane, okay, you just see this one value. Okay. So daripada that value lah, from those that value kita pecahkan kepada plane. Okay, plane. Pecahkan dia. So we divide let's say this A, this A, this B. And this is the bevel gears. And the one is, this is A, this B, this bevel gears. From this direction, we get these two forces. Okay. Then we draw the force. One here, one here. Okay. Another one, we see from here, we just this one. Okay. From here, we just see 1.5. Oh, from here we see both two. This plane, we see this plane, one, this plane, and the one is this plane. And the one is this plane. Okay. So we see this force for this plane. If we see from here. If we see from here, so from this plane, we will get this value. Okay, so how we look on the plane, the force on the plane. So we will determine the reaction force. Okay, the reaction force. So one is this one, and the one we could draw directly for here and here in the middles of the bevel gears. So this, let's say this is the reaction force. Reaction force. From here, this reaction force, RA. Okay. This reaction force. This also the reaction force. So we have this, we know that this, what is the value, this value, this value, this value, this value, this value, this value. So this value, we know already this value is 1.5, same as this one, this value. So we just consider this value, this force, and this force to calculate. So after that, same shear force diagram and moment diagram. From shear force and moment diagram, another one you could proceed, and the one is torque diagram. Shear diagram, moment diagram, and torque diagram, because it has a torque. It has a torque. So from moment diagram, you could identify which is the critical, which area is the critical one. From moment diagram, you could identify which location is the most critical one. Okay, selepas tu next. Okay, then critical, identify critical point. After draw the diagram. Okay, then selepas tu calculate the identify the fatigue stress. Okay, identify the fatigue stress. I think that is quite a bit tricky, because you have axial loads, so then you have bending, then also you have torsion, you have torque. Okay, so you have axial, you have bending, then you have torsion. So once you have calculated this one, same so you may proceed to the because on the shaft there is no discontinuities. Okay, there's no factors. So you need just directly to combine the stress. You have calculated the axial, bending, and torsion. So you have calculated this one, then proceed to equivalence. So then you proceed to sigma EA and sigma EM. Kan? Sebab tak ada notch, tak ada different diameter, so you don't need to calculate this KF. No KF. So the equivalent, combining the load here, combining the stress here, combined. So this is quite tricky, which is axial, bending, and torsion. Okay, once you have calculated this one, so you have to calculate also the endurance limits. So Sn prime, so Cl, Ct, and everything. So after that, then proceed to the equation for Langes and equation for Goodman. Goodman is for fatigue. and Langes is for yield. Then you will get the same procedures. So quite tricky is this value. So if you could calculate this one, you could identify which plane that you see from. So you could get the right reaction force. Then you could calculate the axial bending and torsion. Okay. So you could think of, okay, you could think. Ada soalan kelas sebelum kita end the class? So saya bagi you fikir lah, kan, bagi sedikit